Hello class, in this video we're going to be looking at covalent bonding. The learning intention of this video is for us to define what covalent bonding is. We're going to learn how to actually draw the diagram of simple molecules via a method referred to as the Lewis dot diagram, also referred to as the electron dot diagram. We're going to explore the physical properties of nonmetals, and lastly we're going to be able to explain why metals are able to conduct electricity whereas nonmetals are unable to. So in order for us to understand what covalent bonding is, I think this is a really good analogy or illustration that kind of represents this process. So this image is an analogy of what covalent bonding is. The dogs represents atoms, whereas the bones represents the valence electrons. Using this image as a prompt, I want you guys to see whether you can come up with your own definition of covalent bonding without actually referring to the search engine, and explain how is it different from metallic bonding. So covalent bonding is a force of attraction. So it's a type of chemical bonds that only exist between molecules, okay? And molecules are essentially a group of non-metal elements that are connected to one another. In a covalent bond, what actually happens is that the valence electrons are being shared between the non-metal atoms, so that each of these atoms can therefore follow the octet rule. So as you guys are already aware, most monoatomic atoms, meaning single atoms, they are unable to become stable because they don't actually have a full outer shell. So what actually happens is that when they form a chemical bond with another non-metal atom, these non-metal atoms actually share their valence electrons, and in doing so, this allows each of the non-metals to have a complete outer shell. Just a reminder, guys, but there are three types of chemical bonds. We've already looked at what metallic bonding is, and covalent bonding is different compared to metallic bonding is because not only does covalent bonding only occur between non-metals, which is one of the distinguishing factor, but the nature of the bonding is also different. We know that in a covalent bonding, the electrons are actually being shared, whereas for a metallic bonding, what's actually happening is that the valence electrons are being delocalized and distributed amongst or throughout the actual lattice structure. Now, in order to kind of like represent or show how this is actually happening, this diagram kind of shows it over here with the two, I suppose, pinkish reddish electrons, okay? We know that each chlorine atom has 7 valence on its outer shell, and each of these chlorine atoms require one additional electron in order for it to have the complete outer shell. So what happens is that by showing the electrons in the middle of the atom, this enables each chlorine atom to therefore have 8, because therefore this will therefore have 8, and this will therefore also have 8. And instead of actually representing the electrons using dots, what they do instead is sometimes you could actually use a dashed line, where a dashed line represents shared electrons, and all the electrons are not being shared, are not actually drawn or illustrated at all. This is also another animation that kind of shows you how covalent bonding actually works. And in this particular image over here, they only really show you the valence electrons and the last occupied shell as well. Because chemical bonding only takes place with the valence electrons, that's the reason why we don't really show all the inner shell electrons. It's not really important at all. So as you can see over here, by connecting to each other, now they actually have a full outer shell. And again, this is just another diagram just to strengthen your understanding. The number of covalent bonding that actually occurs or exists between certain molecules is going to be different. So depending on the type of atom that's present, a covalent bond can either be classified as a single covalent bond, and in a single covalent bond, what's happening is that 2 electrons are being shared. So each atom between the neighboring atoms, they share 1 electron each. So therefore, 2 electrons are being shared in total. You could also have a double covalent bonding. And what this means is that each non-metal atom actually shares 2 electrons each. So therefore, 4 electrons in total. And a triple covalent bond is where you have 2 elements sharing 6 electrons in total, 3 electrons each. And that's also represented over here as well. Generally, when we're drawing a single bond, then that's just 1 dashed line. A double bond is represented by 2 dashes, and triple bond, as you can see, is represented by 3 dashes. Now, generally speaking, for instance, for oxygen over here, oxygen is found in the halogen group, so in group 7 or group 17, you could refer to it. If a member of this group is kind of forming a molecule with itself like oxygen, as you can see over here, or sulfur even, then generally these types of atoms will generally form double bonds between each other. All group 3 metals like nitrogen, as you can see over here, if they bond with itself, then they generally form triple bond covalent bonds. I want you to have a go of answering the following multiple choice questions. So this question reads, what types of atoms make a covalent bond? The correct answer for this is going to be nonmetals. The next question reads, which of the following compounds has a covalent bond? In order for you to answer this question, you need to identify which compounds only consist of nonmetal atoms. In this case, that's going to be ammonia, because nitrogen and hydrogen are both nonmetals. This question over here says, why do atoms share electrons? The reason why molecules are formed is so that the nonmetals can actually have an electron configuration of a noble gas, as this makes them stable. And for the very last multiple choice question, how many electrons are being shared in a double bond? The answer is going to be 4. Okay, so this would mean that each atom in the double bond shares 2 electrons each. The next thing we're going to be looking at is how do you actually represent covalent molecules, and there are 2 main ways of doing this. You could either do this by using like the Bohr diagram or the atomic structure, which we've already looked at, where you have to show all the inner shell electrons. But an alternative way of doing that is doing something referred to as the electron dot diagram, also referred to as the Lewis dot diagram, which is the dude who came up with this kind of illustration format, okay? Now, when you do either the Bohr diagram or the Lewis dot diagram, you could either represent the electrons with a cross or with a dot, okay? So it's just up to you guys. But it's really important that you guys understand how to actually represent molecules using both processes. But we're mainly going to be looking at the electron dot diagram. So the electron dot diagram or the Lewis dot diagram are visual diagrams that show the number of valence electrons present in each atom within the molecule, and they also show you the number of electrons actually being shared between the atoms as well. We generally use this kind of visual diagram only to represent simple atoms, so just atoms by itself, or simple molecules, so molecules that only have like a few non-metal atoms that's attached to each other. So over here, you could also draw the Lewis dot diagram showing each individual atom, as you can see over here, and as you can see, they only represent the valent electrons. What I'm going to show you now is how do you actually use the Lewis dot diagram to actually draw simple molecules. So in this simple molecule, we're going to learn how to draw chlorine, okay? So the first step reads, determine the number of valence electrons in each element. We know that chlorine is found in group 7, so therefore it's going to have 7 valence electrons. Now, this is what you would do if you were normally drawing the Bohr diagram, but remember, we're drawing the electron dot diagram. We don't actually need to include the nucleus and all the inner shell electrons, so therefore you can replace all of this like so, okay? So we only really need to illustrate the last shell and all of its valence electrons. What we're going to be doing now is we're going to represent all outer shell electrons with dots or crosses. That's already been done. And the fourth step says connect or pair up these sharing bonding electrons. We know that chlorine needs 1 valence electron in order to become completely occupied. So therefore, each chlorine atom will share 1 electron together. And in doing so, it will now have a full outer shell. So therefore, as you can see here, this is an example of a single covalent bonding, which remember is the sharing between 2 electrons together. The electrons, as you can see here, that are not participating in the bonding process, we refer to them as lone pairs, and other textbooks and other websites refer to them as non-bonding electrons. So this is how you would draw the Lewis dot diagram. As you can see, you don't really need to draw like the rings or the electron shells at all. All you really need to include is just the lone pairs and the covalent bond, which should be represented by a dashed line. Let's now look at another example over here. So in this example, we're going to be learning how to draw the electron dot diagram of water. So water is a molecule that consists of 2 hydrogen atoms and 1 single oxygen atom. And the reason why I've deliberately included oxygen in the center is because when you do examples that contain like an odd number amount of nonmetals. Generally speaking, the nonmetal that requires the most number of electrons to fill its outer shell is generally placed towards the center. So since we know that oxygen requires 2 extra electrons, that's the reason why it's placed in the center. So the first step says identify the number of valence electrons. We know that oxygen has 6 and hydrogen has 1. You can replace all the inner shell electrons. And now the fourth step says just connect all of the bonding electrons together. We know that in this case over here, oxygen requires 2 valence electrons, and in order to do that, what actually happens is that hydrogen shares its electrons with oxygen, and the other hydrogen also shares its electrons with oxygen as well. So therefore, what actually happens is that you form 2 covalent bonds between hydrogen and oxygen. Have a go with answering this question over here. Give yourself 1 minute and then we'll compare our answers together. Now, the correct answer for this one over here, if you've done this correctly, is going to be B. So fluorine has 7 valence electrons, and because it's symmetrical, okay, so fluorine 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Therefore, these electrons over here, they would actually be shared in the center, and in doing so, each fluorine would therefore have 8 valence electrons. I also like you to actually answer these questions over here inside your exercise book. Have a go of answering these questions. You'll find that some of these questions may be a bit difficult, but remember guys, when you've got an odd number amount of nonmetals, generally the one that's in the center is going to be the atom that requires the most number of electrons. Answer these questions, and once you've done it, can you actually just email me what you've done so I could see whether you're on the right track or not. The last thing we're going to be looking at is looking at the physical properties of nonmetals, and some of these nonmetals we've already discussed in previous videos last term. We said that nonmetals are dull and not lustrous, so therefore they have a very dull and very boring colorway. Generally, they're going to be gray if they're in the solid form. When they're also in the solid form, they generally have a low density, so they're very lightweight. They're also very brittle when they're also in the solid state at all as well. We know that most nonmetals exist in the gaseous state, but examples of nonmetals that do exist in the solid state, which is like, for instance, graphite and sulfur, they are generally brittle with the exception of diamond, obviously. And lastly, they are poor conductors of heat and electricity. And what we're going to be able to do, hopefully by the end of today's lesson, is be able to explain why is nonmetals a poor conductor of both heat and electricity. So if you guys can recall, in order for any substance to conduct electricity, there are 2 conditions. You need to have charged particles, and these charged particles must be free to move throughout the actual substance. In this case over here, why do you think nonmetals are unable to conduct electricity based on these 2 properties? Have a go of answering this, and then we'll compare our answers together. So the reason why nonmetals are poor electrical conductors is because that they don't actually have any charged particles that are mobile that can actually carry an electric current, okay? We know that nonmetals and all substances have charged particles. You either have protons, you have electrons, but these must be free to move throughout the actual substance itself. So since nonmetals are held together by covalent bonding, we know that the electrons that are being shared are actually localized, meaning that they are fixed in that position. They don't go around to other atoms in the actual molecule at all. And because they are binded and not free moving, this is the reason why covalent molecules or nonmetals are considered to be insulators of electricity instead. So to show you guys what I mean by this is an example of a molecule over here. And as you can see, these electrons, the ones that are currently being shared at the moment, they are locked in place. They can't freely move throughout the actual substance at all. They're confined to this space. And as a result, they can't actually conduct electricity since they don't have this mobile capacity. Now that we've gone through all the content, what I'd like you to do is I'd like you to please have a go with answering this question over here on the class kick notes. See if you can actually fill in the gaps. I've deliberately not included the actual list of words so that you could try to figure out these words on your own. So try to have a go with this question over here. And also, I'd like you to see whether you could identify whether element W, X, or Y is considered to be a metal, a metalloid, or a non-metal, okay, based on the properties shown in this particular table over here. This is the end of today's video. Thank you for watching. I'll see you guys again in the next video. Peace out. Bye.